Guys, welcome back to TechDose, and in this video we will look at find eventual safe state problem, which is from Leetcode number 802. Let's now read the problem statement. In this problem there is a directed graph of n nodes with each node labeled from 0 to n-1. The graph is represented by a zero index 2D integer array graph, where graph at I is an integer array of nodes adjacent to node I, meaning there is an edge from node I to each node in graph I. That means the graph can be considered to be an adjacency list. A node is a terminal node if there are no outgoing edges. A node is a safe node if every possible path starting from that node leading to the terminal node or another safe node. Return an array containing all the safe nodes of the graph. The answer should be sorted in ascending order. Now, we are given an adjacency list and the name is graph, and it is already given here. So if you can see here, the safe nodes are mentioned to be 2, 4, 5, 6. And how is that? Because if you are starting from 0, then an edge is going to 1. From 1 and there are actually 2 edges going to 2 and 3. So if you consider an edge going to 2, then from 2 there is an edge going to 5, and 5 is a terminal node. So 2 is also fine, and that is why this one can be fine, but there is another edge going to 3, and from 3 there is an edge going to 0. So this is creating a cycle, and 0 is not a terminal node, and that is why there will be a loop. So this is an infinite loop in which this will be present, right? So that is why this 0 is not a safe node, while 6 being alone will be a safe node, right? If you consider this 4, then this is pointing to 5, which is a terminal node, and there is no other outgoing edge from 4. That is why 4 will also be fine, right? 4 will be a safe node. 5 is a safe node, 6 is a safe node, 0 is not a safe node. And if 0 was not a safe node, then everybody in the path of this 0's unsafe cycle will all be unsafe, right? So 0, 1, 3 will all be unsafe, and 2 will be safe because it has only one outgoing edge and pointing to 5, which is a terminal node, and it is safe. That is why 2 will also be safe. So this is the reason why 2, 4, 5, 6 are safe, while in the cycle 0, 1, 3 are not safe. Now let's look at the problem constraint. In this problem, you are having n number of nodes, and the number of vertices can go to 10 to the power of 5 as mentioned. Now each of the adjacency list can be of size n. That means all the other nodes can be adjacent to any one node, and you will find the values going from 0 to n-1, which are the node values. The graph I is sorted strictly in ascending order. Okay, so this will always comply with the answer, because the answer is expecting the answers to be in ascending order. So the adjacency list is already mentioned in ascending order. The graph may contain self loops. This means that there can be an edge going out of 1 and coming into 1. This is called a self loop. And the number of edges in the graph can be maximum 4 times of 10 to the power 4. So if you happen to write a VE algorithm, then you already know V can be 10 to the power 4. And the number of edges can be 4 times of 10 to the power of 4. So this will be around 4 times of 10 to the power of 8. So this will give you a TLE if you happen to write VE algorithm. You have to do something better than this so that your total computations are less than 10 to the power of 8. Okay. So I hope you have already understood the problem statement. So now let's understand what is a safe node. Now if the node is exactly, it does not have any outgoing edge, then it will always be safe. So a node with out degree 0, out degree means the number of edges coming out of a node. If it is 0, then it is a terminal node, and you know in the problem statement that terminal nodes are always safe, and that is why this 0 is safe. Now if you consider the second example, in this case 0 is pointing to 1 and 1 is pointing to 0. So this is creating a cycle. There is no terminal node in a cycle, and therefore all the nodes in a cycle are unsafe. So that is why this node 0 is unsafe, and also node 1 is unsafe. There is no safe node in this graph. If you look at the third example, in this case you will find that 0, 1, 3 are following in a cycle. They are in a cycle. So all the nodes in a cycle will never terminate, and therefore they will be unsafe. So 0, 1, 3 are unsafe. Now any node which is pointing to any of the unsafe nodes, or eventually if in their path there is an unsafe node, then they will always be unsafe. So 4 is pointing to a node which is in a cycle, and since all the nodes in a cycle are unsafe, therefore 4 will also become unsafe. But 2 is a terminal node, so it will always be safe. and the nodes pointing to the terminal nodes will also be safe. So if in a path, it does not matter, like if you are following a path from A, B, C, D, E, whatever, if there is at least one terminal node, let's say E is a terminal node, and all these nodes are safe, that means they are not leading to any cycle, or they are not a part of any cycle, then A will always be safe. So nodes with path not leading to cycle are always safe. Okay, so these 3 points we can derive from the given problem statement. Now we can solve this problem by using the cycle detection technique for the directed graph, because the given graph is directed. But how to detect cycle in a directed graph? If you look at the first graph, we are usually familiar with the two color technique, where we say that 0 is unvisited or false is unvisited and 1 is visited in the visited array. So if you mark all of them with 0, that means initially they are unvisited, and if you start your DFS call to find the cycle, then you will mark it as true, that means this is visited. And if you come here, then you will mark it as true, that means this is visited. If you go here, you mark it as true, that means it is visited. If you come here, mark it as true, that means it is visited. And if you try to go from 3 to 1, then you will say that there is a cycle, because 1 was already visited, right? That is how you find a cycle, and this is actually correct. There is a cycle. But if you use these two colors and try to solve another graph, and I have marked all of them as unvisited, so you will visit it and say it is visited, visit it and say visited, visit 2 and say visited, visit 3 and say visited. Now from 3 there is no outgoing edge, so you will be backtracking to 2, and from 2 you will be backtracking to 1. But from 1, when you again try to go to 3, then you see that it is visited, and so you will say that there is a cycle. But 0, 1, 3 is not a cycle, right? It is not a cycle. But since there was no distinction between the visited node and the processed node, there was no distinction between these two states, and that is why in a directed graph we cannot always say if there is a cycle by just using 2 states. We need 3 states. In an undirected graph there is only 2 states, unvisited and visited. But in a directed graph, even in visited state, there are 2 states, visited and processing, and visited and processed. So these are 2 different states arising from the visited state, which comes under the directed graph only. And that is why to differentiate between these 2 visited states, we need 2 different colors. So I will be taking 0, 1, 2 for them. Now let's start processing using this color technique. So if I assign all these values with 0, that means they are not visited initially. So if I go to 0, I will be marking them as 1. That means it is visited, but it is still under processing. Whenever I reach a node, I will be marking it with 1. That means it is visited and under processing, visited under processing, visited under processing. Now from 3 there are no other outgoing edges. Therefore, just before backtracking, I will mark it as 2. That means I have tried to find cycle from this node, but I could not find it, and I have actually completed my processing. So I'll be going back to 2. Now from 2 there are no other outgoing edges, so I'll be making it processed and move to 1. Now from 1 there is an outgoing edge to 3, so I will try to go to 3. But the value at 3 is 2. This means that we had already processed 3 and we could not find a cycle. So processing via this 1 will definitely again not be finding a cycle, and definitely this is not a cycle, right? So this 2 state is meaning that it has been processed, but if it was under processing, like if the state was 1, then it will be considered as a cycle. Okay, so there is no cycle and you will go back. Now from 1 you do not have any other outgoing edges, so you will be marking it processed. From 0 there is no other outgoing edges, you will be marking it processed, and you are done. So this is how it will say that there is no cycle. So we have to use 3 color for directed graph, and we have to use 2 colors for undirected graph. So I think this makes sense now. So we will be using this technique for this particular problem, since it is a directed graph problem. But for any general node, what logic will we apply is, if you are looking at any ith node and there are n number of outgoing edges from it, and if you are getting a lot of safe edges, that means this path is leading entirely to a terminal node or maybe a safe state. This is leading to a terminal node and safe state. But there is at least one edge. Let's say there is only one edge which is unsafe. That means it is leading to a cycle or some other unsafe node. Then this entire node I will also become unsafe. Because in the problem statement it was mentioned that only if all the outgoing paths are safe, then only the current node can be considered as safe. So ith node is safe if and only if all the outgoing paths are safe. Therefore, you have to find out using DFS or BFS, whatever you do. We will be doing DFS. So using DFS, you have to find out if they are safe, and if all the outgoing edges are safe. If there is at least one edge which is not safe, then you will return false, otherwise you return true. So the combining operator for all the result will be an AND operator, because an AND operation will be actually turning to false if any of the output is false. Okay, so you cannot use any other operator, we have to use an AND operator. So I hope the logic is clear. Now let's look at a dry run of our entire idea. So this is the same example, the first example which was given in Leetcode, and we know that it is a directed graph. So I'll be doing the cycle detection algorithm here, and we will be defining 3 states. 0 means unvisited, 1 means visited, and 2 means processed. So I will be marking all of them as unvisited. So all these values will be marked with zeros. You see, all these nodes will be marked as 0. So I have already defined it in a visited array. And also I will be saving the safe nodes. Okay, what is the meaning of this safe node? It will say that which nodes are safe, and by default I will be initializing all the nodes to be the safe node. And now I will be trying to find out which nodes are unsafe. So what I do is I will always try to make the DFS from 0, because I like to make the DFS call right from the smaller number, and I think most of you will be doing that. So I'll be doing DFS from 0. Now if you start doing DFS, it is only possible if the node is not processed, right? It is not visited. So yes, the state is 0, so it is not visited, right? So you will just mark it as not visited. Now from this 0, in the adjacency list you will be going to 1. So this visit is only possible if 1 is unvisited. So yes, 1 is unvisited, mark it visited and under processing, right? Now from 1, where can we go? We can go to 2. We can only go to 2 if it is unvisited, right? So we can mark it as visited. From 2 we can go to 5, and we can mark it as visited, right? So from 5 there is no other outgoing edge, and since from 5 there is no other outgoing edge, that means it is safe. So 5 is already marked as safe, and what it will return in the recursion call, it will be returning a value true. That means this node 5 was safe. So from 2 there is no other outgoing edge, and since it got true from one of its outgoing edges, which is the only outgoing edge, therefore this 2 will also remain as safe. We will not mark it unsafe, right? And so while backtracking we had to mark it as 2, that means it is processed. This will also be processed, and now we will backtrack to 1. Now this 1 will receive a true from a call to the node 2. Okay, so one of its edge is safe, but there is another edge which is going to 3. So we have to test this node 3 as well. So let's make a call to this 3. It is only possible if this is unvisited. So mark it as 1. It is visited and under processing. Now from 3 as well there is an outgoing edge, and an outgoing edge is going to 0. Now if you look at this 0, you will see that it is visited but under processing. It is not processed, right? So there is a cycle. So this means this 3 becomes unsafe. So mark this node as false. That means it is unsafe now. And there is no other outgoing edge from 3. So mark it as visited and processed, and this will be returning a false value to 1. Now 1 got a true value from 2 and got a false value from 3. So that is why this 1 will be marked as false immediately. Okay. And even if there are more outgoing edges from 1, I will not be processing them because I have found a false here, right? So why do I need to process them? So I can just go back. I can return back to 0 and return a value false. Now 0 got false from 1, so it will also be marking it as false. So this is also unsafe, and there is no other outgoing edge from 0, so you will be marking it as 2. That means it is visited and processed. So you can accordingly change your visited array here. I am just showing it in the graph how the changes will happen, right? So 0 state has changed to 2, 1 state has changed to 2 as well because it has been processed, 3 state has changed to 2, 2 state has changed to 2, and 5 state has also changed to 2, right? Now we have done DFS from 0. Now we will try doing DFS from 1, but it is already processed. If it was 0, then I will perform DFS. So I cannot perform DFS from 1, 2, 3, but we will start DFS from 4. Okay, because this is unvisited. So what I will do here is I will mark it as visited and under processing. Now when you look at this 5, when you try to make a call to 5, 5 will not make any further call because it has already been visited and processed. So look at the value stored at 5. Look at the value stored at 5. So it is already storing us a solution which is true. It is just like your dynamic programming approach, where you actually pre-process. Whenever you solve a sub problem, you save it so that next time when it hits, then you don't have to solve it again. So in this case, we are saving the result, right? So it will be sending a true value directly without having to solve anything. Even if it had more edges, it will not solve it. Okay. So it will directly return a true. So 4 had only one outgoing edge. It does not have anything else. So therefore this 4 will become a safe node and this will mark as true. Okay, so 2 means it is processed now, it is safe. Now I will try a DFS call from 5 and I cannot make it because it is already processed. I will try DFS call from 6, so I'll mark it as 1. But from 6 there is no other outgoing edge, so I'll mark it as 2 and backtrack, so it is also safe, right? So 4 state is 2 and 6 state is also 2. All the nodes have been visited and processed, and therefore after doing this entire process, if you iterate through the safe nodes, whichever nodes you are finding true, those all will be the safe nodes. You can just iterate and record all these nodes 2, 4, 5, 6. And when you record all these nodes from left to right, then they will always be in ascending order as the question is demanding, right? Return the answer in ascending order. So your answer for this case will be 2, 4, 5, 6. I hope you were able to understand this. In this particular case, since we are doing simple DFS, in which if we are processing a node, we are not processing it again. So the time complexity is going to be order of v plus e. So since v can go to 10 to the power 4, e can go to 4 times of 10 to the power of 4. So adding these two values, it will be approximately 10 to the power 4, right? So it is well within 1 second limit. And the space complexity will be order of v, which is due to the visited array as well as due to the safe nodes, right? Both are equal to the size of number of vertices. Therefore, the time complexity is order of v plus e, space complexity is order of v. Let's now look at the code. If you are someone who is looking to prepare for top product based company within a limited time of just 3 months, then we have brought for you both the DSA and the system design live interview training program. The most important feature of this program is you get a filtered and condensed structured curriculum, in-depth discussion of all the topics, and my guarantee of your understanding, one-on-one guidance with me, and live weekend classes. To know more about the training, you can WhatsApp us on this given number. If we look at the driver function, which is eventual safe nodes, we are given the adjacency list in the form of graph. I will be finding the number of nodes and I will be defining the safe nodes. So safe nodes have been made global inside the class. So I am just reassigning it a size of n and pre-filling all the values with true. I am defining a visited array with n size and marking it as 0. That means everything is unvisited. The other states are 1 means visited and 2 means processed. Now I will be applying DFS from each of the node. So if the node is not visited, then I will try to visit it. So this is the check safe state call, which is the DFS call, and sending the graph visited and the current node from where I want to do the DFS. So if you look at the check safe state, in this case, whenever I reach to a node, I will be marking it as visited. So set the state to 1 and I will be taking the is safe state to be true. Now I will be going to all the neighbors using the adjacency list in the graph. I will be going to all the neighbors of the current node and I will be checking if the neighbor is unvisited, then I will try to visit that node and get the return value and apply an AND operation into the is safe state. Otherwise, if the neighbor is already visited but under processing, this means this current edge is creating a cycle. So if it is creating a cycle, then return false and save the result into the safe node of the current node, because the current node has now become unsafe, right? And we are saving it just like the dynamic programming approach, so that the next time when somebody asks that is this current node safe, then I can simply return saying that it is not safe, right? Now if the neighbor has already been processed, then I can just take the state whatever is saved in from the safe nodes, because it has already been processed, so the answer must be present in the safe nodes array, right? So I'll be directly taking without doing the DFS call. So this will be optimizing the number of DFS calls we make. And finally, once we have traversed all the neighbors, I will be coming out and I will be marking the current node to be 2. That means it has now been processed just before backtracking. And then I will be saving the result for the current node in the safe nodes array and marking it with the is safe value, and simply this will end my entire DFS call. and then again I will be checking for further nodes to see if that node is unvisited. I will again perform the DFS. So once all the DFS calls have been made, the safe nodes array will have true for all those nodes which are safe, and it will have false for the nodes which are unsafe. So I can simply take a result array, iterate through the safe nodes array, and if the value is true, then I will push it into the resultant array. And finally, I will return the result. So this is the entire approach, and I hope you were able to understand it. If you still have any doubt, then feel free to comment below and I'll try to help you as soon as possible. Like and share our video and subscribe to our channel in order to watch more of these programming videos. See you guys in the next video. Thank you.